we'll now do some tutorial on the linear regression part. Okay, so I think I should just give a brief overview. Just a sec. Okay, so just last. So our goal is to learn this linear model. Given these orange dots that we have, these are the data points. Given the data point, we want to fit a line such that it best explains the data points. Now, this line, when you want to learn a line, there is this two variables that you want to identify. This is theta naught and theta one. You want to identify what is the best theta one and theta naught that explains this data point. Okay, so let's look into this part now. So we have this. We first import all the packages. This scikit linear model also has directly has linear regression to solve this exact same problem. This, if you use the scikit linear regression model library, it will identify automatically theta naught and theta one for you. But we will not use this for the timing. We will use the exact calculation. First, show how to do this thing, and then we will show that you can directly use this linear regression package and solve the same linear regression model. Okay, so let's look into this process. So we have some data set. Now this is a diabetes data set. We now created label X, and now this is the diabetes label Y. For each corresponding X, we have corresponding Y that we want to predict. Now, if you see that label X has multiple features, there is one age feature, sex feature, BMI, BP, and S1 to S6. Some feature S1 to X6 is also known to us. And we have just printed the top five. You can print, I think if you just put n equal to 100, you can actually see all 100 different features. If you just set 20, so you can see all the 20 features that are there. So these are the 20 people's feature. Each row that you see is a feature of a single individual, and corresponding diabetes value is also available to you. So diabetes Y, if you look at the 20th people, so it has diabetes of 68. Okay, so you can these are the data set. This is your X. This is given this information. What would be the diabetes of that person is the one that you want to predict, and that diabetes is 151. Can you tell me whether it's a whether it is a classification problem or a regression problem? Can someone tell whether it's a classification problem or a regression problem? How will you solve? So each row.
We have label X and Y, so it's a classification one.
Okay. Anyone else? So each row here is the information about a person, and the corresponding value is the label is the information about that person. Whether how much diabetes does this person have? As someone has as you one of you has pointed out, it can be solved through classification too. There is nothing wrong that you cannot solve through classification, but you can see that the numbers can go from 0 till as high as, okay, let me just, as high as 350 or even 400. So these are all from 0 to 400. There is sufficiently large bag size, large set of numbers. So you can solve through uh, classification problem. But since the size of the set itself is very large, we will prefer a regression problem. We'll consider this problem as a regression problem just because the set is sufficiently large. It's a continuous values, right? Remember, it is 151.0 is there, but it can be 151.52. So it's a continuous value and it's a very large set. even though it looks like for a real number here, but it's actually it looks like all integers, but it's a real number with proper decimal numbers too. So it can be as large as possible. So it's easier, matlab it's best model if it is a regression model. Okay. uh, does it justify, were you able to follow that why this is a regression model fits better here? Simply because the set is sufficiently large and it's on a continuous value. Okay, so let's first solve this problem. Let's first assume that you only have a singular value x. X is a scalar, not a vector. X is a scalar. Theta naught plus theta 1 times x, some scalar x. It's not a vector, it's a scalar x. So for scalar x, we just simply chose a S3 information. Like only this information is known to you. For every person, only this information is known to you, S3 information. And with this information, only this information, you want to predict how much diabetes this the person has. So S3 feature of S1, if only given to you is minus 0.043, you have to predict the person has a diabetes of 151. If a person 4 has S3 feature 0.00814, the person 4 has a diabetes of 135. So you only have this information and you need to predict its diabetes. So only given this feature, that's what X is, you just chose the S3 feature. This S3 feature you chose the diabetes information, that these are the diabetes information. So now you have X and Y. So let's look into X. So you have this X. For every person, you have this X information and its corresponding Y information. Okay, Y is the diabetes of that information. Now let's plot this information in a file. So you have this X information. So this is BMI is what is the set. S3 is this information that you see here. S3 is a BMI information. That's what this data set is. And Y is uh, the level of diabetes that you have. So if you plot this, and this is how the image looks like. So you can see that BMI of 0.05 can have a diabetes of say 45 or 25 till as high as 300. So the point that you should be seeing is that just by a single x, it's very difficult to fit a linear line. Probably you may actually fit a linear line like this with a negative slope. That will explain the data set. Otherwise, this data is all over. So it has so much of randomness, and just fitting a single linear line may not be able to explain this data set properly. And this is what we will see now. Okay, so we have x and we have y, and we want to predict a line that best explains the data set. And the line should be somewhere like this, a negative slope line. Okay, now let's look into this. So we will actually try to minimize this least square equation. So you have this uh, h is equals to x theta naught plus theta 1 x minus yi is the actual value and whole square, and you want to minimize this. The best way, since it's a quadratic equation, you can actually see this will become a very big quadratic equation, and quadratic equations can be minimized with exact values. The minimum value, I don't have to tell you, the quadratic equations can be exactly minimized. So this will become a quadratic equation and you can minimize, find the minimum value for this theta naught and theta 1. Okay, so once you expand the quadratic equation and you solve, the line, the theta naught and theta 1 equation simply becomes this. Okay, here we call it alpha and beta, but this is how it looks like. Beta theta naught is your beta and alpha is your theta 1. Okay, so it's simply y is equals to alpha x plus beta. That's what it is. And once you actually solve this equation, so alpha turns out to be a very simpler equation, sx by ssx. So what it is that you first calculate the mean of x, y is the mean of y. So you just calculated the mean x and mean y. And then you can calculate the sum of square SXX, which is the variance of in X. So if you see, this is what the variance is here. Now SXY is the covariance between X and Y. So X and Y covariance, and SYY is the variance in Y. So now once you have SXY and SXX, you can divide these two to calculate alpha, and beta is simply difference between Y minus alpha X. That's what it is. So now you have your alpha. Your alpha has such a very negative, uh, negative, what is it called? Slope, as you can see, and beta has also a very large value of 152. Okay. So now you were able to plot x and y. So you have your x and y function. Now what we will do is that we will use this alpha x plus beta to predict the values for x. So this predict function just simply takes your x and then predicts what is the prediction. So it will use alpha x plus beta model to predict what would be the diabetes score. And this print function will simply print the values that this is what was there and this is the actual one, measured progression measured, progression predicted, and error. So progression measured is the true value, progression predicted is the prediction from the predicted model, and the error is the difference between them, progress measured minus predicted. So it will simply just print the data for it. Now the scatter plot, we will see the scatter plot. We'll come to this part later a bit. So let's do this. We will just predict for all x, this x information that we had, which was these data points. Since we are fitting a line in this, and we got a negative slope too. So these are the x's. We will send these x's and try to estimate the prediction value. So we are sending each x's in the predict function and predicting what is the predicted predicted diabetes for each individual x size. And then we will try to print the predictions and see what it happens. So this is how it looks like. The first person had a predicted diabetes of 151, but we predicted 179.87, and the error is minus 28. It's a very high error though. The measured of the zeroth person, this is first person, is 75, and the predicted was 104.57. So error is minus 29. So you can see that the model is still making a lot of error here, right? And you were able to see so because even a best fit line will not be able to explain all these variations, because the data you cannot explain with a single straight line all these variation. It is very difficult for a single straight line to measure all such variations. So okay, so this is how it looks like. Now the plot function that we are seeing here is this. So in this y-axis that you see is the predicted value. What is the predicted value and what is the measured value? So in the best scenario, what you want is that it should fit this straight line, that whatever was predicted and it was also measured, it should actually perfectly match. And if it perfectly matches, it will be on a this it will follow this straight line, this red straight line. All the data points should lie on this perfect straight line. If your measured and prediction are perfectly correct, it will all the points will lie on this straight line. But as you can see, it does not lie on the straight line. It just simply varies everywhere. The prediction is 150. Is someone saying something? Okay, so if the predicted value is 150, the measured value is all from 25 till 350. So you can see that it lies all on these lines though. So if it was a truly perfect model, if it was predicted was 150, the measured should also be around 150, and then it will all follow the straight line. If it perfectly fits, all the data points would lie in this perfect straight on this red line. But since the model is incorrect, It is not lying on the straight line. It is lying somewhere randomly placed, or most likely it is completely incorrect. You can see that the error is very high. Right? That's what this plot shows to you. So I will wait for a while here before I move to more discussing of linear regression with vectors. Is this till this part? Were you able to follow? I'll see if there are any questions here. Okay, let me see if there are anything on chat. Okay. So any question till this point? Okay. So I will just repeat this again. If the prediction model was correct, it would have all lied on the red line. If the prediction model is absolutely perfectly correct, it will all lie on this red line. Since it is not a good model, that's why we do not see that it is lying on this red line. It is lying on straight somewhere, scattered everywhere. Now, in this example, we used only x as a scalar. We only had one data point, S3, to predict diabetes of this person. Now, let's look into what if we have not a single x, but actually a vector there. Okay. Okay, before we go there, so this is a visual way of saying that this model is not correct. How will we actually measure the error though? So one way is to measure an error is find the absolute mean average error. So what you do is that you take the average of what is the error between them, and you just take the average of that error. Okay, it simply do an average of the error. The other is mean squared error. You actually take the square of the error and then average it to say whether how much is the error. And the other one is root mean squared error, where you actually take the square of the error, calculate the average value, and apply a root over this. Why? Because the inside value is still calculating average error square, and root over that will give you the actual average error. So we call it root mean squared error. This is mean squared error. What is the mean of the squared error? And this is the root mean squared error. So what is the mean squared errors under root? So all these matrix are a correct way of calculating this information. So that's how we will calculate now. So so you can see that this is, you first calculate the y and y predicted, the square of this. Oh, this is not needed. Sorry, this is. So MAE, the mean average error, is that you calculate the average, the predicted, no, the true y and the predicted y is difference. This is the error term. You can sum over all the error, divide by the n, divided by n, the total number of points that are there. So length of y, that will give you the average error. So mean average error. Similarly, we have error square sum divided by n. So this will give you the mean squared error. This is the square of error and the mean value of that. RMSE, the root mean square, you just simply apply a square root over the mean squared error. Now, if you actually calculate, so this is how the mean average error looks like. I think this is, wait a sec. It should be np.apps. Okay, let me first explain what I did. So in this case, if you see just the mean average error, it says that it is very small. But the mean squared error says that it is very high, and the root mean square error is also sufficiently high. The error is, on an average error you are making is 70, which is sufficiently very high. If a guy has uh, what is diabetes of 50, you may end up predicting 50 plus 70, 120 of a diabetes. So the error itself is sufficiently very high, which is close to 50. But can someone point me why is mean average error so low, even though our metric does not show that the model is super incorrect? But why is this mean average error so low? Shouldn't it be like very high number like mean squared error and root mean squared error? This number should also be sufficiently high. Can someone tell me why are we seeing a very low number here? Very small. It's when you see e power minus 14, just assume it's 10 power minus 14. So minus 1.59 into 10 power minus 14 into 10 power minus 14. It's that small. Can someone tell me why are we seeing mean average error such a low number, even though our model did super poorly? The other errors like the mean squared error and the root mean error shows a very large error, but the mean average error is very small. Can someone point me why is this the case? Why are we seeing such a small number here? Okay, so the reason that we are seeing such a small number is because look at the calculation that we are doing. We are just averaging the error term. So if one error could be in a positive direction, which is that you predicted very low number, but actually the diabetes was very high. So if the diabetes was 170 and you predicted 70, so you have an error of 100 in one case. In other case, your diabetes is very low and you predicted very high. Your diabetes is 70 and you have predicted 170. So the error is minus 100. But when you calculate the average between these two, 100 minus 100 is 0. So the average will become 0. That's how the mean average error is a very is not used in general. What we use is mean absolute error. So this what we actually use. This was just for you to know. So what we actually use is the mean absolute error. We rarely use mean average error. We don't use. I don't have never used mean average error. What we use is mean absolute error. So what you do is that you calculate the absolute value of the error. So only the positive part you will take and calculate the average between them. So what it becomes is, even though some numbers are say minus 100 error and some are plus 100 error, both will become 100 and 100 error. And when you calculate the error will be still be 100. So what you use is mean absolute error. And now if you see, the error is around 60. Now it says that the error is sufficiently high. Okay, so we this part I will just go back to what it was before. We rarely use mean average error. Mean average error does not give you what you want. What you should be looking is mean absolute error, mean squared error, and root mean squared error. Mean average error is not the correct thing that you should be looking at. So let's just add a new term. Okay, I see. Okay, so now you see the mean absolute error is 59.33, mean squared error is this large, and our root mean squared error is this much, and mean average error is a very low number. Okay, so in general, we never use mean average error. I don't think I have we ever use though. So most of the time you will either see mean absolute error, mean squared error, or root mean squared error used almost everywhere. So yeah, this is what it is. Uh, till this point, does anyone have any doubt? Now you have a matrix to judge whether this model is doing properly or that model is doing properly. One way was to visually verify that this model is poor, that model is poor. Now you have a matrix to measure that whether which model which you should prefer, whether you should prefer this model or someone else or something else. Okay. So if no one has doubt, then I will move ahead with now linear regression with a vectors now. So now you see here, where did our slides go? Okay, so now you have this x naught, theta naught plus theta 1 was there. Now, what if there are multiple x's? So there is not just one x, but multiple x's, x1, x2, x3. As you saw before, let's see. Now you see, sorry, I need to run this. So now you see, this is not nice. Diabetes x dot head. So now a single person consists of so many features, right? A single person has so many age, sex, BMI, BP, S1, S2 to S6 features are there. So what if we learn a linear regression model on this? So how will it look like? It will look like beta naught plus beta 1 times age, beta 2 times sex, beta 3 times BMI, beta 4 times BP, beta 5 times S1 till beta 7 times S6. So you will continue adding beta in each of these terms plus beta naught, and that's what it looks like now. So if we actually make all betas, if we now need to find all the betas in this such that that explains this data point y. So the y is still the diabetes, but now we have made a simple excess now. Now we have beta. Okay, so now you have to see what how it looks like. So now you have this thing beta naught times x naught. So this x naught is assume that it is 1. In x naught, generally whenever you see x naught x1, x naught is here set to 1. You can always convert this beta naught times x naught plus beta 1 times x1 into a matrix forms. Remember the linear regression, linear algebra class where you can always write this linear equation into a matrix form equation. So it will simply become y equals to x times beta. So x is simply a row vector and beta is your column vector. So beta has this beta vector will have beta naught, beta 1, beta 2, beta 3, and x will have x naught, x1, x2, x3, and then when you multiply these two vectors you will get this linear equation. Now once you have converted into a set of linear equation y equals to xb, now you can solve for beta, right? It's simply just x inverse y, and that's a fancy way of writing x inverse. This is like a pseudo inverse. Now is x transpose x inverse. So if you just take inside inverse, so it will become x inverse x transpose inverse, and you have x transpose here. So x transpose inverse times x transpose is identity. Simply becomes x inverse y, which is beta is equals to x inverse y. And that's how you write. You just simply write this x transpose x inverse. So x transpose into x, that's inverse of this into x transpose into x transpose into y to calculate beta. So now you have calculated beta, and the prediction model is simply y prediction is equals to x times beta. That's it. And if you see how your prediction have done, so the first person has BMI, diabetes of 0th person has a diabetes of 151. You ended up predicting 600, 206. The second person has a diabetes of 75. You ended up predicting 68. The error is 6. So the error has become, some errors are still very high, but some errors have reduced now. Let's look at how the model looks like now. As you now see, this has lower error because now it is actually starting to show up on this red line, but still the error is still sufficiently large, right? The error is still sufficiently large for prediction of this diabetes. Now let's look into the metric that we have calculated. So how does this metric looks like? So we have now mean absolute error 2. So now this is how the matrix looks like. The mean average error is still very low, which we should ignore simply because it does not give you any information. Mean absolute error has reduced from 59 to 43. Squared error from 5000 it has reduced to 2800, and root mean square error from 70 it has reduced to 53. Now you can see that you will prefer this model over the previous one. Visually, it also seems like it is correct because the predicted and the measured have started to match this red line. And in matrix 2, you see that the numbers are much lower than the previous errors. I will wait here for a while to see if there are any doubt here. Okay. I thought people would have doubts here, but it's okay. If you are able to follow, then it's nice though. Okay, now let's use the scikit package. Now we have this X, which is this large X that you saw. Let me just write it again. Diabetes X dot head. So you have this information X and the corresponding Y, the diabetes Y. Now let's directly fit a linear regression model. So this is X and this is Y. You convert into a NumPy array and then you fit linear regression model with intercept, which is beta naught. And you fit the model with the data set X and Y, and you get these coefficients. And this is what you also get in beta too. Let me just print beta in the next line itself. If you write beta, so you see minus 10.098, minus 10.098, minus 239, minus 239, 67.62, 67.62, and the intercept is beta naught, and this is 152.133. You have 152.133. So beta and this everything matches perfectly. So the beta is the one that you calculated through this equation, this equation that you used, x transpose x inverse times x transpose, and that's how, if you just have used this linear regression model, you'd have got the same information. Okay, let's just print beta here, beta. So you have the same model coefficient and the model intercept. Intercept is simply beta naught, and that's what your beta naught is here, and everything, all these information is beta 1 to beta n is here. Now if you use this model to predict, so you see that the here too, the first prediction that it makes is 126, and that's how we also saw the first prediction it also made was 206.11, even though the person had a diabetes of 151. Here too you see 206.11, but the person has a diabetes of 151. So that's how you can do beta naught and beta prediction. Now we used mean absolute error and mean squared error. We actually calculated through manually, but you can use the scikit-learn package to calculate the mean absolute error and mean squared error. So you see the mean absolute error is 43. As we also saw, the mean absolute error previously was also 43.27, and the squared error was 2859.69. So if we use these model 2, we get the same number, exactly 43.277 and 2859.69. So we get the same exact numbers even from the scikit-learn package. Okay, now the data splitting, we will not be covering data splitting because I have not yet covered data splitting part. So we will do this part of the tutorial, even though it is there. I will do this part of the tutorial maybe next class. So I will not be covering this, but I will be covering this in next class. Till this point, I have just covered how to use scikit-learn for your linear regression model, how to use scikit packages to evaluate your model with mean absolute error and mean squared error. What is the internal functions of these mean squared error and mean absolute error, and how do you calculate? How do you uh, calculate these beta naught mathematically and programmatically without using the scikit-learn package tool? So this was the entire tutorial for today. I was expecting more questions though, but it's okay if everyone is able to follow, then it's nice. Yeah, so this is for today's tutorial. I will share the entire tutorial on the chat. Please wait. In the meantime, if anyone has any doubt, please uh, uh, raise though. Or if you had any doubt in yesterday's class, something you were not able to follow, something if you were not able to follow, uh, is everyone able to follow properly, or am I going too fast? Should I increase the pace? Because today I thought that there will be more questions, so I did not prepare. If this is the if you are able to follow, then I will add more tutorial information there. We'll do more examples or more difficult ones. Uh, so people are able to follow properly, right? Okay, I just shared linear regressions tutorial that we did today. Can someone confirm if they can see the tutorial? If they can download the tutorial though, not just see. Can someone confirm something? If they can see the tutorial? Okay, thank you. Thank you, Parmila. Pramila. Okay, Pramila. No, sir. Uh, no, what problem are you facing? Uh, no, sir. You're not able to see the tutorial. Okay, what you have to do is you have to download that tutorial. Uh, this linear regression thing, you will not be able to see it directly, but if you download it, and then you need to open it in a Colab notebook. Okay, let me actually show it to you how to do this thing. How to see this? How to do people know how to actually put this Colab notebooks on Google Colab? Okay, please let me know if my screen is visible. I will show it to you how to do this thing. Okay,
Yeah,
so when you hello.
yeah, it is visible, sir.
Okay. I think some of you have don't know how to open this Colab notebook. Let me just give a brief thing. So when you go to this link, this is how it will show, and you need to press this download button. or you can just open with Google Colab is also there. So if you just press this part, it will open that notebook in a Google Colab. Let's see if it can. Yeah, that's how you will be able to open. You see, can now everyone see that they can open this linear regression in a Google Colab notebook, and if you start running your, you need to connect, and then you start running these things. You will start. It will start running. So I'm connecting with the Google Colab. It's taking time. Just a sec. It got connected. Let's see. Okay. So this is able to connect. This is also able to connect. And you see, we have all these information again. So if you start running, you will be able to run. So you will be able to plot these data points in Google on Google Colab too. So you see all these informations are. You should be able to run this thing exactly the same way that we run. Now, can someone confirm that they are able to see their Colab notebook, this notebook, and run these Colab notebook once? Anyone should be okay. If they can do, then I will assume that okay, you are able to do this thing properly. Hmm. Is anyone trying? Are you able to see the Colab note, download the Colab notebook or open the Colab notebook on? Okay, yes. Aha. Thank you. Thank you, Shobika. Okay, at least someone has confirmed that they are able to do the same. And if you are still not able to do, we will do it again. And if you, what specific problems did you face? We can discuss tomorrow again. Uh, so today I was able to finish 10 minutes before. Okay. Anyway, so if you are still facing the trouble with seeing these notebooks on Google Colab, we will discuss the same again in the next class. And else, if you are all able to open the notebook and do the experiments there, that's well good. That's what the intention is. If you are able to do it by yourself, then it's really nice. And please let me know if this pace is too fast, too slow. Should I add more examples, or else everyone is able to follow? The pace is okay. Okay, seems like the pace looks okay. Okay, okay then. See you in the next class then. Thank you again. So we can end the lecture today. Uh, Thank you.